Hi everybody, we're going to be working on the end of the notes for chapter 5. So we're going to talk about constant pressure calorimetry, and this is the same type of experiment that you'll be doing in the lab. So the idea here is that you can carry out a reaction in an aqueous solution, and you use a device like what we refer to as a calorimeter to isolate the reaction from the surroundings. And so then the idea is that any of the heat that's either expelled or absorbed during the reaction stays inside of the container. So we can essentially measure the heat change of the solution that's formed in the cup and determine what heat was released by the reaction itself. So if we know the specific heat of the solution formed, which is typically very close to the heat of, or the specific heat of water, then we can calculate delta H by calculating the heat as mass times specific heat times the change in temperature. So this is a problem that's very similar to a problem that we'll be doing in the lab. Just going to move this up a little. So this talks about 50 mils of 1 molar hydrochloric acid and 50 mils of 1 molar sodium hydroxide are mixed together in one of those coffee cup calorimeters. And when that happens, the temperature inside the cup increases from 21 to 27.5 degrees. So we're going to calculate delta H for the reaction that takes place. So this is a double displacement reaction, a neutralization reaction, and we're going to calculate it eventually in kilojoules per mole of water formed. So we're going to make the assumption that the calorimeter itself has what we refer to as a negligible heat capacity. And what that means is the amount of heat that's absorbed by the calorimeter is so small that we can ignore it. And we'll also assume that the solution has a density similar to water and a specific heat that's similar to water. So we'll start by writing the reaction. So hydrochloric acid and sodium hydroxide goes to sodium chloride and water, and that is balanced at this point. So the assumptions that we're going to make here are that the sum of the heats adds up to 0. And my heats are the heat that would be absorbed by the calorimeter plus the reaction plus the solution. Those all have to add together to be 0. And you can see, though, that one of the assumptions we made was that the calorimeter's heat is negligible. So if I get rid of that term, then the sum of the heats are still 0, but all I have is the heat released or absorbed by the reaction and the solution. So I can set one equal to the negative of the other, and then I can plug in the data from the paragraph that you have up there. So we have a total volume in the cup of 100 mils. We have a density of 1 gram per mil. That gives me my mass. Then I multiply it by the specific heat I was given and by the temperature change. So delta T is the temperature change. And it's final minus initial. So it would be 27.5 minus 21.5. So I end up with 2,700 joules for that. Now the problem is that that's not really what I was asked. All right, so I was asked to try and figure out how much heat was released per mole of water formed. That's this idea of heat being extensive. So what we need to do is match the heat released in our experiment to that reaction that's written. So I got to think about how many moles did I have. So I can go back and look at the volume and the concentration of the HCl. So there's 50 mils times 1 mole per liter times 0.1 moles of water per mole of HCl. And I just realized I left off the conversion between milliliters and liters to get 0.05 moles of water formed. So we'd also have to include in here that I have to change milliliters to liters. So I have to divide by 1,000. So we get the same number of moles of water if we start with the NaOH. So I have a negative 2,700 joules. That's what we got on the last slide, divided by the number of moles of water that were formed, or minus 54,000 joules per mole. And then I converted that to kilojoules per mole because that's typically the way that values are given. All right, so move on to our next slide. So another method that's used for reactions that release a lot more heat is what we refer to as bomb calorimetry. So bomb calorimetry is carried out in a sealed reaction vessel. We refer to it as a bomb. It's not really a bomb. Basically what you have is a metal container that's filled with water. Your sample cup is down in the bottom of the water in an isolated container, so it's down here. And then you have wires that are connected to that, basically that are connected to an igniter. And this inner container is filled with oxygen, and then you carry out a combustion reaction inside of there. There's a stir that basically keeps everything at an even temperature throughout. So in this case, the heat that's released or absorbed by the water and the contents of the calorimeter is a good approximation of the enthalpy change of the reaction. So our terms are a little bit different. We still start out essentially with the same idea. So we're going to do a problem to look at the heat content of methylhydrazine. So methylhydrazine is a liquid rocket fuel. The unbalanced reaction is given here above. And the idea is that if we put 4 grams of methylhydrazine in the bomb calorimeter, and we know the heat capacity. So remember, the heat capacity is something we would have to measure through a different experiment. So it's not something I would look up. It's for the object. So it's specific to the calorimeter that's being used. So the heat capacity is given as 7.794 kilojoules per degree Celsius. And the temperature of the calorimeter and its contents, increases from 25 degrees to 39.5 degrees. So in order to calculate the heat release, we're going to do the same kind of calculation we did before. We're going to start by saying the sum of the Q's are equal to 0. But this time, the only 2 heats that I have to keep track of are the calorimeter itself and the reaction. So Q of the reaction ends up being equal to the minus Q of the calorimeter. And I can replace the heat of the calorimeter with the heat capacity of the calorimeter times the change in temperature. So I plugged in the heat capacity of the calorimeter, and then I multiplied by the change in the temperature, and I got minus 113 kilojoules. Now that's the actual heat released. That's not how much heat would be given per mole of methylhydrazine. So if I want to calculate it per mole of methylhydrazine, then I have to go back and do the same kind of calculation where I take the heat that I measured, which is down here, all right, and I divide it by the mass of the methylhydrazine, the 4 grams. And then I converted grams to moles by using the molar mass of methylhydrazine. So I just looked up the molar mass of CH6N2. And I get negative 1.30 times 10 to the 3rd kilojoules. So this is a method that's used frequently to determine the heat released by fuels and even foods. So a lot of times you can actually calculate the heat or the energy that's contained in certain foods. A lot of times calorie contents are also derived this way. If I can't carry out an experiment, then one of the other things that I can do is I can calculate delta H values based on tabulated values. So there are a lot of reactions where delta H is well known, and it's convenient to measure delta H for a reaction by looking up delta H values for reactions that we've already measured. So we can calculate delta H by using published values. So we do that using what we refer to as Hess's law. So Hess's law talks about the idea that if a reaction is carried out in a sequence of steps, that delta H for the overall reaction is the same as it would be if I carried the reaction out in individual steps. So this is again because delta H is a state function. So the total enthalpy change depends only on the initial and final conditions or states of the products and the reactants. So if you look at this reaction, you've got methane and oxygen turning into carbon dioxide and water. So here on the outside, we've got this happening in one step. All right, and I get minus 890 kilojoules. Another possibility is to carry it out in 2 separate steps where I only partially oxidize the methane in the first step and then finish oxidizing it in the second. And the idea is that these two heats that I measure for these two steps are the same when I add them together as the total that I got if I carry it out in one step. So a lot of times what we do is we use values that are referred to as enthalpies of formation, and we can put those together, the enthalpies formation for the materials that are in a reaction, in order to calculate the enthalpy change for a reaction. So a heat of formation reaction is when I make a compound from its elements as they occur at room temperature and pressure. So if I was going to write a heat of formation reaction for glucose, I would look at the elements that are in glucose. There are 6 carbons, 6 hydrogens, and 3 oxygens. And remember, oxygen and hydrogen are diatomic, so I had to write them as H2 and O2. And make sure I balance it. I have to leave a 1 in front of the C6H12O6. So this is always for 1 mole, forming 1 mole of the material. So if I'm not sure what state these are in, all right, I would have to look that up. Or I'm going to show you how to use Appendix C, which will give you a good idea of what state each of these materials would typically be in at room temperature and pressure. So I want you to try and do the same thing now for the heat of formation reaction. See if you can write it for iron 3 oxide. You can pause the video. So iron 3 oxide is Fe2O3, iron with a +3, oxygen with a -2, Fe2O3. And I can make that 1, I have to leave a 1 in front of the Fe2O3, so I need 2 irons. And because oxygen is diatomic, I would actually write this as 3/2 O2 goes to Fe2O3. So this is a heat of formation reaction. The values that go with these reactions are tabulated. So these are what we refer to as standard enthalpies of formation. So my enthalpies of formation are measured at standard conditions, 25 degrees Celsius, 1 atmosphere of pressure. And they're typically given in kilojoules per mole. So this is just a little piece. You have a listing in Appendix C. So Appendix C in your textbook will have delta HF values for several different compounds. And then what we can do is we can use the heat of formations of these compounds to calculate the heat of formation of a reaction. So let's think about a combustion reaction. We're going to look at the combustion of propane. So C3H8 and oxygen goes to carbon dioxide and water. So what I want you to do is to kind of think about this as occurring maybe in some steps. All right, so Hess's law says if I can measure the heat for those steps, I can add them back together. So let's pretend that we start, so I'm going to look at my reactants here. So let's pretend that we start with our reactants, and then we go up and we turn them essentially into the elements that they came from. So I take C3H8 and oxygen and I break it apart into carbon and hydrogen and oxygen. So that's going to require a certain amount of energy. That's my decomposition. And then I take my reactants and I form my products. So I form the CO2s. And then I take my hydrogens and my oxygens that are left over and I form my 4 waters. So if I add these 3 steps together, all right, decomposing my compounds and my reactants into the elements, and then turning them into carbon dioxide, and then turning them into water, if I add these 3 steps together, then I get the overall heat for that reaction. So by looking up the heat of formation of the materials that are in there, there's a simple way to kind of put this together for any reaction. So what we find is that if we can look up the heat of formation of materials in the reaction, then the heat of the reaction is going to be equal to the sum of the heats of formation of the products minus the sums of the heat of formation of the reactants. And the N and M that are in here, these are the coefficients that are in the balanced equation.